Everybody, take a look at the front board. First page. At the top, write down the basic rule. If you have two equal sides, that means that you have 45, 45. That's the basic layout or model. X doesn't have to be a whole number. When X is a whole number, then this is a very easy style problem. It's when X is a fraction or already has a radical in it that you get the more difficult questions, because you're attaching a radical to no matter what X is. So when I see number 1, I see 45, 45. The first thing I do is put in slash marks. I put a 4 here to match up with the other 4. That is a nice match with my model because I have a whole number where X is. So all I'm doing is placing 4 times radical 2. The model is just a shortcut, because if I have a 4 and a 4 and an unknown hypotenuse, then I could do Pythagorean theorem. I could do c squared equal to 16 plus 16, c squared equals 32. I could use the square root of 32, and the pattern develops because you will always end up using this number in this spot, which will go back to this number. So that number will always appear in the answer, and you'll always get a radical 2 attached. So you can go through the process for a 45-45 through the Pythagorean theorem, or you can just follow this pattern, 4, 4, 4 radical 2. Thank you. So would you call number 2 an easy style question? Does it have whole numbers with where the x's are in my pattern? 6, 6, what's this? 6 radical 2. Up here, if it helps, sometimes people get bogged down with the variable. That variable is different than the variable I'm using up here. You could just think to yourself, empty box, empty box, empty box. All 3 of those spots contain the same quantity. Number 3 matches the pattern. We've got something times radical 2. So I'm going to place a 3 here and a 3 here. When you get to a problem like number 4, you can use the Pythagorean theorem. You can do 14 squared equal to x squared plus x squared. These two are the same, so I can put 45, 45 in there. What is x squared plus x squared? 2x squared. Then I do a little bit of division. It gets me to 98. I still got to do a square root. When I do the square root of 98, that breaks down into 49 and 2. That breaks down into 7 radical 2. So I can go through that whole process to get 7 radical 2. Or when I have a whole number where I usually am used to seeing a radical, just cut it in half and attach a radical 2. But you can always fall back on just doing the Pythagorean theorem if it's a 45, 45, 90. When it's 30, 60, 90, your options are a little more limited because you don't have 2 equal sides. Remember way back, what did I say should be the first thing you do when you look at the 30, 60, 90? What should you find?
Short side.
The short side. Locate the 30, point to the short side. Everything hinges on the short side. If you've got the short side, it's usually a pretty simple problem. If you've got the short side and it's a whole number, then it's a super easy problem. Because what do I do with that short side if I want the hypotenuse?
Double it.
Double it. So that's a 4. What do I do with the 2 to get the longer leg?
Attach radical 3.
Attach a radical 3. Done. So knowing the short side is a good thing. Knowing the hypotenuse is a good thing. Here's your hypotenuse. I'm still locating my short side. If I double to get the hypotenuse, then I cut the hypotenuse in half to find the short side. Now I have this to figure out my leg. That would be 3 radical 3. Short side, I don't have. Hypotenuse, I don't have. But the radical 3 is appearing where I normally think of it, as being located in my model. If I have 6 radical 3, I know that whatever's in front of the radical is the short side. Then I can take that and double it to find my hypotenuse. So those first 3 still follow the general pattern. Let's go back to the top for a second. At the top, let's actually draw the pattern. Empty space times radical 3, 2 times empty space. You can put variables in there, you can put x's in there if you want. Short side, long leg, hypotenuse. The last one requires a little more work. If you're ever lost, realize that this originally came from an equilateral triangle. So if you forget your pattern, just create another triangle next to it and realize that the original figure was equilateral. So if it's equilateral, you know that that's M, and you know that that's M, but you also know that this entire length originally was N. So what is this? Well, it looks like it's half of N, and it is. That's why we take this and divide it in 2 to find the short side. So if you're ever lost, draw on an equilateral triangle just to figure out where everything is coming from. We normally would see a radical 3 over here. So what do? Normally, I would take this, and then I would attach a radical 3 to it. And then I would take this, whatever it is, and multiply by 2. Well, you take whatever's there. In this case, we've got an M. Normally, I would take this M and attach a radical 3. But 5 is already there. M times radical 3 must be equal to that 5. How do you get rid of that radical 3? What do you do, Zane?
You divide them both by radical 3.
Divide by radical 3. This is a perfectly legitimate answer, but not with mathematicians. They don't like the radical on the bottom. So I've got to do something like this. That gives me 5 radical 3 over 3. Can you reduce 5 over 3? No. That is your answer. That is M. If you can't reduce that, or reduce the whole numbers within it, you're gonna get a complicated looking fraction, and that's okay. We were solving for m. We made it pretty on the bottom with the whole number. We just couldn't reduce it. I leave it in that form. How do we get from the short side to the hypotenuse? What are you supposed to normally do? Well,
Multiply it by 2.
multiply it by 2. So instead of 5 radical 3 over 3, we get 10 radical 3 over 3. So m turned out to be this fraction. N turns out to be this fraction. If you can reduce them at all, you do. In this case, we can't. Keep that somewhere in your SQL review section.